Dear ladies and gentlemen, on behalf of the National Aerospace University Kharkiv Aviation Institute, I would like to invite you for participation in our course Micro and Nanotechnologies for Protective Coatings Deposition. The role of coatings in modern equipment applications is increasingly important. High operating temperatures, new alloys and component life requirements all drive the need for more durable system. A component designer is more and more using new coating systems to help provide the environmental protection needed for these more stringent demands. Producing solid ceramic components is not always the best approach to solving wear or corrosion problems. In many cases, taking the original metallic part and applying a coating can be the best solution. Coatings can vary from few microns to few millimeters and be deposited by different means. The coatings, its thickness and means of deposition will depend on the final use of the components and the environment it has to resist. It is a fact of life that many components are deemed to be worn out when their surfaces have degraded beyond a predetermined limit. This limit may vary from the appearance of minor pitting or scoring marks in bearing surface to the removal of several millimeters of material from the bucket of an excavating tool. However, the useful life of many components which are unsuitable to be made from advanced ceramics may be extended by coatings with a material tailored to resist the particular environment in which the component is working. These include thermal barrier coatings as used in gas turbines and on piston crowns in large diesel engines, low friction and anti-seizing coatings as used in lubricant-free bearings, wear-resistant or hard-facing coatings as used for treatment of valves and in internal combustion engines, and finally corrosion-resistant coatings as used in the chemical industry. Coatings may be applied by many different techniques, with coating thicknesses varying from several microns to several millimeters. Thin coatings are usually applied by physical vapor deposition or PVD, chemical vapor deposition CVD, and chemically formed processes CFP, with other technologies, for example high velocity oxyfuel HVOF, plasma and flame spraying together with plasma transferred arc, weld overlaying and laser cladding being used to deposit thicker coatings. Selection of the best coating for an application is not often straightforward. Selection based on hardness or form standard wear testing would indicate coatings like HVOF, tungsten carbide and cobalt, plasma sprayed chromium oxide ceramics, or fused coatings as giving the ultimate performance. Indeed, these coatings do provide the best solution to many applications, but they are certainly not universally suited to all applications. Other factors must be considered. Among them are cost, life expectancy, corrosion, counter surface, effect of processes on substrate material, surface finish of profile, temperature, lubrication, abrasives, loads and speeds, impact, shock or fatigue, ability to work harden, coefficient of friction, porosity. Among other specific coatings properties that may be required are thermal barrier or conductor, electrical insulator or conductor, non-magnetic, special surface profiles, abradable, requiring erosion resistance but sacrificial to counter surface, abrasive, required to abrade or grip counter surface, very low coefficient of friction or non-stick properties. On the table presented on the next slide, you may find typical coatings functions. In the first column, and coatings, corresponding coatings applied in the second column. So if you want to reduce wear, titanium carbide or nitride should be applied. For reduction of friction, better to use PTFE or molybdenum disulfide. For increasing friction, titanium or bonded abrasives should be used. If you want to improve lubrication, copper and lead will suit best. For increasing temperature of load capacity, electroless nickel should be applied. To prevent adhesion, you should use silver or gold plate. For embed particles, indium and lead will suit best. For reduction of corrosive wear, you should take chromium plate or diffusion. To retain fluid lubricants, phosphating or nylon will be best solution. For rebuilding surface, steel hard surfacing should be used. To reduce surface roughness, silver plate. To prevent drop erosion, polyurethane or neoprene should be applied. For prevention particle erosion, cobalt alloy or molybdenum should be used. For different types of metals, specific surface treatment should be applied. For example, for aluminum, you should use chrome plating, anodic coating, phosphate, chromate, conservation coatings, and some others. For steel, vapor deposition, chrome plating, phosphating, ion nitriding, induction hardening, flame hardening, and liquid nitriding should be applied. The demands for engineering coatings are becoming more and more stringent. Environmental concerns are also being considered as an integral part of the design process. Thermal spraying is an attractive coating technique as it offers a wide choice of materials and processes that have a reduced impact on the environment when compared to conventional plating processes. Thermal spray coating technologies such as flame spraying, wire arc spraying, and plasma spraying allow many problems of wear, corrosion, and thermal degradation to be resolved by engineering the surface with a tailor-made coatings. Compared to traditional surface modification processes, thermal spraying offers greater thickness capability, no part size restrictions, it produces minimal noxious waste. High processing temperatures allow deposition of many high melting point materials onto a relatively cold substrate. Thermal spray technology allows part to be made from less expensive, lighter or weaker base materials while providing the performance of a metallic, carbide, ceramic or ceramic materials. Rather than crafting the entire part from a premium robust material, a thermal spray coating can yield the same or better performance for a significantly lower investment. All thermal spraying processes rely on the same principle of heating a feedstock, or powder or wire, and accelerating it to a high velocity and then allowing the particles to strike the substrate. The particles will then deform and freeze onto the substrate. The coating is formed when millions of particles are deposited on top of each other. These particles are bonded by the substrate by either mechanical or metallurgical bonding. Generally speaking, the process of thermal spraying could be divided into 4 main steps. The first step of any coating process is surface activation. This is done by cleaning and grit blasting the surface to be coated. Masking techniques are normally adopted for components that only need specific areas to be coated. The second step is to melt the material. This is done by introducing the feedstock material into the hot gas stream. The hot gas stream is produced by either a chemical reaction like combustion or by a physical reaction like plasma. Thirdly, the particles are then accelerated to the substrate by the gas stream and deform on impact to form a coating. And finally, the coatings are inspected and assessed for quality by either mechanical or microstructural evaluation. A common feature of all thermal spray coatings is their lenticular or lamellar grain structure resulting from the rapid solidification of small globes flattened from striking a cold surface at high velocities. The bonding mechanisms at the thermal spray coating substrate interface and between the particles making up the thermal spray coating is an area which in many cases is still subject to speculation. It generally suffices to state that both mechanical interlocking and diffusion bonding occurs. It is used to think that thermal spray coatings bonding mechanisms include mechanical keying or interlocking, diffusion bonding or metallurgical bonding, and other adhesive, chemical and physical bonding mechanisms, oxide films, van der Waals forces, etc. Among the factors affecting bonding and subsequent building up of the coatings are cleanliness of the substrate surface area, surface topography or profile, temperature or thermal energy, time, reaction rates and cooling rates, velocity or kinetic energy, physical and chemical properties, physical and chemical reactions. Cleaning and grit blasting are important for substrate preparations. This provides a more chemically and physically active surface needed for good bonding. The surface area is increased, which will increase the coating bond strength. The rough surface profile will promote mechanical keying. Individual particle cooling rates on impact can be of the order of 10 million degrees Celsius per second. Thermal interaction is obviously very limited, important with regard to diffusion bonding, temperature and time dependent. Increase in thermal and kinetic energy increases chances of metallurgical bonding. Temperature, velocity, enthalpy, mass, density and specific heat content, etc. Thermal spray materials like molybdenum, tungsten and aluminum metal composites produce so-called self-bonding coatings. These materials have comparatively high bond strength, increased metallurgical or diffusion bonding, and can bond to clean polished substrates. Higher preheat temperatures for the substrate increase diffusion bonding activities, but will also increase oxidation of the substrate, which could defeat the objective of higher bond strength. High kinetic energy thermal spraying using HEP, HVOF, and cold spray procedures, high bond strengths due to energy liberated from high velocity impacts, the high density tungsten carbide, cobalt, and cold spray coatings are good examples. Metallurgical or diffusion bonding. The combustion wire thermal spray process, formerly known as metallizing, flame spray and metal spray processes, was first invented in 1910 by Schoop in Switzerland. The flame spray process is basically the spraying of molten metal, ceramics and ceramides, can be used in rod or composite wire form, onto a surface to provide a coating. Material in wire form is melted in the flame, oxyacetylene flame most common, and this heat source creates a gas stream with the temperatures in excess of 3000 degrees Celsius with correctly balanced conditions between oxygen and acetylene, and atomized using compressed air to form a fine spray. When the spray contacts the prepared surface of a substrate material, the fine molten droplets rapidly solidify, forming a coating. This flame spray process carried out correctly is called a cold process, relatively to the substrate material being coated, as the substrate temperature can be kept low during process, avoiding damage, metallurgical changes, and distortion to the substrate material. This flame spray process has been extensively used in the past and today for machine, element work, and anti-corrosion coatings. Materials sprayed by this method are zinc and aluminium for anti-corrosion cathodic coatings on steel, nickel, aluminum composite wire for bond coatings and self-bonding coatings, molybdenum for bond coats, molybdenum for hard bearing applications, excellent resistance to adhesive wear, used on piston rings, synchromesh corners, and journals. High chromium steel for many applications requiring hard and wear-resistant coatings. Bronzes, babyite for bearing applications, stainless steel, nickel, and monel for anti-corrosion and wear. Aluminium, nickel and aluminium for heat and oxidation resistance. Among the process advantages are low capital investment, simple to operate, wire form cheaper than powder, deposit efficiency is very high, possibly still best for applying pure molybdenum coatings for wear resistance. Portable system, preheating facility built in unlike arc spraying, possible to use system in areas without electricity supply. Among the process disadvantages, the following may be mentioned. Limited to spraying materials supplied in wire or rod form, not capable of the low oxide, high density and high strength coatings of plasma and HVOF. Next process is combustion powder thermal spray process or flame spray process, also known as powder flame spraying and LVOF, low velocity oxygen fuel process. This process is basically the spraying of molten material onto a surface to provide a coating. Material is powder form, is melted in a flame, oxyacetylene or hydrogen, most common, to form a fine spray. When the spray contacts the prepared surface of a substrate material, the fine molten droplets rapidly solidify, forming a coating. This flame spray process carried out correctly is called a cold process relatively to the substrate material being coated, as the substrate temperature can be kept low during the processing, avoiding damage, metallurgical changes, and distortion to the substrate material. The main advantage of this flame spray process over a similar combustion wire spray process is that a much wider range of materials can be easily processed into powder form, giving a larger choice of coatings. The flame spray process is only limited by materials with higher melting temperatures than the flame can provide, or if the material decomposes on heating. The following process is high velocity oxy-fuel, or HVOF. HVOF spraying has been developed principally to produce high-quality metal and carbide coatings equivalent to the degun process and with superior properties to conventional flame spraying processes. HVOF is a thermal spray system utilizing the combustion of gases such as hydrogen or a liquid fuel such as kerosene. Fuel and oxygen mix and atomize within the combustion area under conditions that monitor the correct combustion mode and pressure. Mixing of the gases occurs inside the gun and the externally ignited flame reaches a temperature of about 2700 degrees Celsius. Powder materials is injected through the flame and the molten particles projected at velocities approaching 2000 meters per second onto the workpiece. One of the basic rules of spraying is that high combustion pressure equals high gas velocity, high particle velocity, and resulting high coating quality. Precise control of all spraying parameters and powder feed rates and the use of a robot to precisely position the gun enables high quality coatings to be repeated on a large variety of different components. One of the key benefits of these systems, high velocity, is the extremely high coating density and low oxide content. The low oxides are due partly to the speed of the particles spending less time within the heat source and partly due to the lower flame temperature of the heat source compared with alternative processes. Main applications of this process are rotary knives blades, aero engine parts, gate valves, pistons, and shafts. General HVF coating characteristics are high bond stress, more than 83 MPa, high density, low porosity, low oxide content, high hardness, fine as sprayed texture, able to be ground or lapped to a fine finish 0.1 to 0.2 microns, excellent resistance to wear by abrasion, erosion or fritting. At present, these available coatings consist mainly of the coatings based upon tungsten carbide and cobalt, chrome carbide and nickel, as well as stainless steel, aluminum, bronze, and others. The next process is arc wire. This form of thermal spraying uses wire material as a feedstock. An electric arc is used to provide the heat source by utilizing two current-carrying wires, also called twin wire arc. As the wires are fed towards each other, the electric current short circuits between the wires, creating a temperature of around 4000 degrees Celsius. This process is an economical thermal spray technique for the application of metallic coatings that are high in internal porosity, from 10 to 15%. This temperature arc wire process is widely applied for deposition of wear-resistant coatings, corrosion-resistant coatings, thermal barrier coatings, component restoration, and other areas. Materials which are typically deposited are ceramics and metals. Another popular technique of coating deposition is plasma spraying. This plasma spraying process involves the latent heat of ionized inert gas, or plasma, being used to create the heat source. The most common gas used to create the plasma is argon. This is referred to as a primary gas. Atmospheric plasma spraying, or APS, uses plasma under atmospheric pressure to melt and protect the powder used for the coating. The heat generated in APS surpasses 10,000 degrees Celsius, which allows the melting of virtually any materials. Applications of this method include wear resistance, corrosion resistance, thermal barrier coatings, component restoration, and others. Typically used materials are ceramics and metals. The vacuum plasma spraying technology uses plasma under low pressure, approximately 0.1 atmosphere, inert conditions to melt and project the powder used for the coating. The heat generated in VPS surpasses 10,000 degrees Celsius, which allows the melting of virtually any material. This operation is performed in a controlled inert environment, resulting in a high-quality coating with low porosity, less oxidation, and a superior adhesion. Applications are wear resistance coating, corrosion resistance coatings, thermal barrier coatings, net shape forming, and others. Among the applied materials, we could find ceramics and metals. The detonation thermal spray process efficiently uses high kinetic energy and temperature of detonation wave and controlled thermal output to produce dense, very low porosity coatings that exhibit very high bond stresses, some exceeding 350 MPa. The coatings have low residual, fully controlled internal stresses and can be sprayed to thicknesses not normally associated with dense thermal sprayed coatings. The detonation gun basically consists of a long water-cooled barrel with inlet valves for gases and powder. Oxygen and fuel, acetylene for most common, is fed into the barrel along with a charge of powder. A spark is used to ignite the gas mixture, and the resulting detonation heats and accelerates the powder to supersonic velocity down the barrel. A pulse of nitrogen is used to purge the barrel after each detonation. This process is repeated many times in a second. The very high kinetic energy transferred to the particles by the detonation process, some exceeding 1,200 meters per second, the coating material generally does not need to be fully melted. Instead, the powder particles are in a molten state and flatten plastically as they impact the workpiece surface. The result are coatings with more predictable chemical composition and very homogeneous with a fine granular structure. This method uses for parts which work in super heavy modes and aggressive media. The benefits of detonation coatings are very high coating thickness, low porosity, excellent adhesion, optimized micro-hardness, low oxide metallic coatings, preloaded properties of layer. Among the typical applications may be found rebuild and salvage operations, abrasion or erosion resistance, sliding wear resistance, resistance to fritting, gulling or adhesive wear, resistance to chemical attack. Vapor deposition is a process in which the substrate workpiece surface is subjected to chemical reactions by gases that contain chemical compounds of the materials to be deposited. The coating thickness is usually a few micrometers, which is much less than the thickness provided by other techniques. The deposited materials may consist of metals, alloys, carbides, nitrides, borides, ceramics, or various oxides. The substrate may be metal, plastic, glass, or paper. Typical applications are coating, cutting tools, drills, reamers, milling, cutters, punches, dies, and wear surfaces. There are two major deposition processes, physical vapor deposition and chemical vapor deposition. These techniques allow effective control of coating, composition, thickness, and porosity. Physical vapor deposition, or PVD. The three basic types of physical vapor deposition PVD processes are vacuum or arc evaporation, PV or ARC, sputtering, and iron plating. These processes are carried out in a high vacuum at temperatures in the range of 200 to 500 degrees Celsius. In physical vapor deposition, the particles to be deposited are carried physically to the workpiece rather than by chemical reactions, as in chemical vapor deposition process. In vacuum evaporation, the metal to be deposited is evaporated at high temperatures in vacuum and is deposited on the substrate, which is usually at room temperature or slightly higher. Uniform conditions can be obtained on complex shapes. In PV arc, which was developed recently, the coating material, cathode, is evaporated by a number of arc evaporators using highly localized electric arcs. The arcs produce a highly reactive plasma consisting of ionized vapor of the coating material. The vapor condenses on the substrate anode and coats it. Applications for this process may be functional, oxidation-resistant coatings for high-temperature applications, electronics and optics, or decorative, hardware, appliances, and jewelry. Titanium nitride, for example, is deposited in partial vacuum by feeding ionized titanium into a plasma or of ionized argon and nitrogen. The operation occurs at a temperature of between 350 and 450 degrees Celsius, with the resultant Tn growing on the surface of the workpiece. Materials such as titanium carbonitride, chromium nitride, and tungsten carbide and carbon can be produced by changing the materials in the crucible and the reactive gases. PVD coatings, because of the process is carried out in a vacuum chamber, there are issues of size limitations of the workpiece. In addition, the process is effectively line of slight to deep holes and bores cannot easily be coated. In sputtering, an electric field ionizes an inert gas, usually argon. The positive ions bombard the coating material, which is typically cathode, and cause sputtering or ejecting of its atoms. These atoms then condense on the workpiece, which is heated to improve bonding. In reactive sputtering, the inert gas is replaced by a reactive gas, such as oxygen, in which case the atoms are oxidized and the oxides are deposited. Carbides and nitrides are also deposited by reactive sputtering. Very thin polymer coatings can be deposited on metal and polymeric substrates with a reactive gas, causing polymerization of the plasma. Ion plating is a generic term describing the combined processes of sputtering and vacuum evaporation. An electric field causes a glow discharge, generating a plasma. The vaporized atoms in this process are only partially ionized. Chemical vapor deposition, or CVD, is a thermochemical process. In a typical application, such as the coating cutting tools with titanium nitride, the tools are placed on a graphite tray and heated to 950 to 1050 degrees Celsius at atmospheric pressure in an inert atmosphere. Titanium tetrachloride, a vapor, hydrogen and nitrogen are then introduced into the chamber. The chemical reactions form titanium nitride on the tool surface. For coating with titanium carbide, methane is substituted for the gases. Chemical vapor deposition coatings are usually thicker than those obtained from PVD. A typical cycle for CVD is long, consisting of 3 hours of heating, 4 hours of coating, and 6 to 8 hours of cooling to room temperature. The thickness of the CVD coating depends on the flow rates of the gases used, time, and temperature. In electroplating process, the workpiece, which is cathode, is plated with a different material, anode, while both are suspended in a bath containing a water-based electrolyte solution. Although the plating process involves a number of reactions, basically the metal ions form the anode, are discharged under the potential from the external source of electricity, combine with the ions in the solution, and are deposited on the cathode. All metals can be electroplated, with thicknesses ranging from a few atomic layers to a maximum of about 0.05 millimeters. Complex shapes may have varying plating thicknesses. Chemical cleaning and degreasing and through rising of the workpiece prior to plating are essential. The parts are placed on racks or in a barrel, bulk plating, and lowered into a plating bath. Common plating materials are chromium, nickel, cadmium, copper, zinc, and tin. Chromium plating is called out by first plating the metal with copper, then with nickel, and finally with chromium. Hard chromium plating is done directly on the base metal and has a hardness up to 70 HRC. This method is used to improve wear and corrosion resistance of tools, valve systems, hydraulic shafts, and diesel and aircraft engine cylinder lines, and also for rebuilding worn parts. Brush electroplating process, or selective plating, is a method of electroplating from concentrated plating solutions on selected area without immersion tank. The solution is held in an absorbent material wrapped around an anode. Electrical contact is made by brushing or swabbing the part cathode with the anode. It is also called brush plating. Faraday's laws of electrolysis applied to selective plating. Brush plating equipment: DC power supply, brush plating machine; anode and anode holder, selective plating suppliers; solutions or chemicals for selective plating chemicals; containing and transferring. Benefits of brush plating or selective electroplating are: prevent or minimize disassembly of workpiece. Portable equipment allows on-site work. Plate large parts or other parts not easily tank plated. Supplement tank plating, minimize masking. Restore worn, corroded or mismatched parts, mismachined part. Improve soldability, EMI, shielding, conductivity in selected areas. If comparing with tank electroplating, brush electroplating has some advantages and disadvantages. Some electrochemical processes as tank electroplating, but a different method of application. Brush plating chemicals are more concentrated. Brush plating uses higher current densities, faster buildup of metal deposit. The brush-plated deposit can be more dense, less porous. Precision build-up easier with brush plating. Brush plating equipment is portable. Among the electrodeposited materials could be found alloys for magnetic applications, materials for corrosion and wear protection, electrodeposited semiconductor materials. That's it for an introduction to the course of micro and nanotechnologies for protective coatings depositions. If you have any questions, please write them in the comments and contact to our representatives. Thank you for your attention and goodbye.